So what I have over here is a circuit with a resistor and a capacitor in series with the battery. And initially the switch in the circuit is open. And now I'm going to close the switch just like this. And when I close the switch, the battery is going to produce a current that flows in this direction right here. It's going to flow clockwise. And so now what I want to do is I want to analyze different scenarios of the circuit immediately after the switch is closed, as well as a very long time after the switch is closed or at steady state. And so let's analyze the first question, which says immediately after the switch is closed, what is the voltage across the capacitor? So let's draw the capacitor plates right here. And so all I did was I just redrew these two capacitor plates that are in the circuit. And so notice how when I close the switch, the current is going to flow clockwise. And when the current flows clockwise, the initial charge on the capacitor plates is going to be 0. And the reason why it's 0 is because immediately after we close the switch, the current doesn't put any of its charge on the capacitor plates, or in other words, the current doesn't have enough time to put enough charge on the capacitor plates immediately after the switch is closed. So, or another way to think about it is that the capacitor plates, the potential difference between the capacitor plates is 0 because the charge on the capacitor plates is also 0. So there's no potential difference between the capacitor plates. And so the formula that we have for the voltage across the capacitor is just the charge on its plates, Q, divided by the capacitance of the capacitor. But notice that we said that the charge on the capacitor is 0, so this term goes to 0. So the voltage across the capacitor is 0. And the reason why the charge on the plates is 0 immediately after the switch is closed is because the current immediately after we close the switch doesn't put any charge on the capacitor plates because it doesn't have enough time to put any charge on the plates. And without any charge on the plates, that means that the voltage across the capacitor at t equals 0, or immediately after we close the switch, is just 0. And so another way to think about this is that since the voltage across the capacitor is 0 at t equals 0, or at time equals 0, the capacitor acts like a wire, or it acts like a normal piece of wire at time equals 0, or immediately after we close the switch. And that's because the voltage across the capacitor at time equals 0 is 0 volts. And since the voltage across the capacitor is 0, remember that the voltage across a wire, like a normal piece of wire, is also 0 because a wire doesn't have any resistance. So the voltage across a wire is 0. So another way to say this is that the capacitor acts like a wire, or it acts like a normal piece of wire at time equals 0, or immediately after we flip, or immediately after we close the circuit. And remember that, just to reiterate, the charge on the capacitor plates is 0 initially because the current doesn't put any charge, or it hasn't put any charge on the plates, on the capacitor plates at time equals 0. So the voltage across the capacitor at time equals 0 is equal to 0. Now notice how earlier I said that the capacitor acts like a piece of wire at time equals 0. So I can just replace this capacitor right here that was on my diagram with a piece of wire, because the capacitor acts like a piece of wire. So if I redraw the circuit, I can just replace the capacitor with a piece of wire. See, look, notice how there I drew in just a piece of wire instead of a capacitor. So this is how the circuit behaves immediately after the switch is closed. And that's because the capacitor acts like a normal piece of wire at time equals 0. So this is how the circuit behaves at time equals 0, since the capacitor doesn't have a voltage drop across it. Now let's answer the second question. Immediately after the switch is closed, what is the voltage across the resistor? Now notice how at time equals 0, the capacitor acts like a wire. So we can just ignore the capacitor and just look at the resistor. And I circled the resistor here in this diagram. And so the capacitor acts like a normal piece of wire at time equals 0. And so when the current is running, or when the current is flowing through the circuit, all of the battery's voltage is going to be dropped across the resistor. Or in other words, the voltage of across the resistor is equal to the voltage of the battery at time equals 0. And so the reason why the battery's voltage is equal to the voltage across the resistor at time equals 0 is because we're treating the capacitor like a piece of wire. So it's almost as if the capacitor doesn't exist at time equals 0, because we're just treating it like a piece of wire. And also, since the capacitor acts like a piece of wire, the voltage across a piece of wire is 0. And so that's why we can ignore the capacitor right now. And so the only thing remaining in the circuit is the resistor. So the voltage drop across the resistor is equal to the voltage of the battery. So we can write an equation for that. So the voltage of the battery is given by the EMF of the battery, and that's equal to the voltage across the resistor at time equals 0. And so that's the answer for number 2, that the voltage across the resistor is equal to the voltage across the battery, which is equal to the voltage of the battery, which is EMF of the battery. And that's all due to the fact that we can ignore the resistor for now because it acts like a piece of wire at time equals 0. Now let's answer the third question. Now the third question isn't at time equals 0. Instead, it's at steady state. Or in other words, this question happens after a long time after the switch is closed. And notice that we're looking at the process at steady state and that the charge of the capacitor is not changing. And so the charge of the capacitor at this point is remaining constant at steady state. And so this is long after we close the switch. And so since the charge of the capacitor plates is not changing, the capacitor plates reach a final charge denoted with Q subscript F for charge final. And so this is the final charge on the capacitor plates. So what we can write is that at steady state, the capacitor plates hold a maximum amount of charge, and we're denoting that maximum amount of charge with Q subscript F. So since the plates hold a maximum amount of charge, what this means is that if the plates hold a maximum amount of charge, it means that the capacitor doesn't need any more charge. And so what it actually does is that the capacitor stops the current in the circuit from flowing. And so at steady state, the current in the circuit is 0 because the capacitor has a maximum amount of charge, and so it doesn't need any more charge, so it actually prevents any charge from flowing, or it prevents any current from flowing in the circuit. That's why the current is equal to 0 at steady state. And another thing to note about steady state is that remember that we initially said that the voltage across the capacitor at time equals 0 was 0, but now at steady state, the voltage across the capacitor is equal to the voltage of the battery, which is denoted with the EMF of the battery at steady state. And so the potential difference across these two capacitor plates is just equal to the voltage, is just equal to the EMF of the battery, or the voltage of the battery. So we can actually redraw this circuit above. And so note that I said that the current is equal to 0 at steady state, meaning that there's no current that's flowing in the circuit at steady state. So actually, the capacitor, it acts like an open circuit, because in an open circuit, the current cannot flow. So this is what the circuit acts like at steady state. The capacitor acts like an open circuit. And so the capacitor acts like an open circuit, meaning that no current is flowing in the circuit at steady state, since the current is equal to 0. And so if in an open circuit, or if a switch in a circuit is open, that means that the current cannot flow in an circuit with the open switch. So the capacitor at steady state acts like an open switch, and so that actually prevents the current from flowing. And the reason why it does that is that because the capacitor plates at steady state, they're holding a maximum amount of charge, which I denoted with Q subscript F, and that actually prevents any more current from flowing in the circuit. And so since the capacitor plates are holding a maximum amount of charge on their plates, they don't need any more charge, so that's why the current equals 0. So the capacitor acts like an open circuit at steady state. And so the answer for the third question is that the current in the circuit at steady state is 0. Now let's answer the fourth question. In the steady state, what is the charge on the capacitor? Now remember that we said that at steady state, the charge on the capacitor is at its maximum value, which I denoted with Q subscript F for charge final, or Q final, which is the maximum amount of charge. And so at steady state, what we can write is a formula for the voltage across a capacitor, which is just the charge on its place divided by the capacitance. And remember that I said that at steady state, the voltage across the capacitor is equal to the voltage across the battery. So this voltage of the capacitor is just equal to this voltage across the battery, which is given by EMF of the battery. So the left-hand side of the equation is equal to the voltage of the battery, and we're trying to find Q final, which is the final charge, and that's divided by the capacitance. Now let's just solve for the final charge, and we get this. We get the voltage of the battery times the capacitance of the capacitor. And that's the final charge on the capacitor plates. And so since the capacitor at steady state is holding the maximum amount of charge, which we just found, that's the reason why the capacitor prevents any more charge from flowing in the circuit, because it's already holding a maximum charge. So it doesn't need any more charge, so it'll just prevent any current from flowing in the circuit. So that's why the current is equal to 0 at steady state. And now I want to just redraw what the circuit looks like immediately after the switch is closed. And so remember back when I answered the first and second questions, I said that since the charge on the capacitor plates at time equals 0 is 0, that means that the voltage across the capacitor is 0. So the capacitor essentially acts like a wire at time equals 0. So it looks like this diagram right here that I just drew. So the capacitor just acts like a normal piece of wire. That's why I replaced the capacitor with the piece of wire. Now let's look at it at steady state, or where the current is equal to 0. And since the current is equal to 0, remember that we said that the capacitor plates at steady state are holding the maximum amount of charge, so it doesn't need any more charge from flowing in the circuit. So the capacitor acts like an open switch or an open circuit, which I drew in right here, and that's what causes the current to be equal to 0. And the current at steady state is 0, and that means that the current at time equals 0 is when the current is at its maximum value. So the current is at its maximum value at time equals 0, and then it diminishes or it decreases as it approaches steady state, because at steady state the current is equal to 0. Now let's answer the final question. We need to use Kirchhoff's loop rules to obtain expressions for the charge of the capacitor and the current in the resistor as functions of time. Now, in order to use Kirchhoff's loop rules, we have to pick an arbitrary starting point on our circuit, and let's just make this red dot on the circuit that I drew. Let's make that the starting point. And so notice how the current in the circuit is going in the clockwise direction. And so I'm going to travel from the red dot in the clockwise direction, in the same direction as the current. And so if I go upwards, or if I travel clockwise, the first thing I'm going to encounter is the battery. And notice how there's a negative terminal of the battery, and there's also a positive terminal. Now, since I go clockwise, I'm going from the negative terminal to the positive terminal of the battery. So I'm actually gaining the voltage of the battery since I'm going clockwise. So I chose the positive terminal of the battery since I'm going clockwise. And then after the battery, I encounter the resistor. Now, since I'm going in the same direction as the current, there's going to be a potential drop across this resistor. And so that's why I put a negative sign, because there's a potential drop, or there's a potential difference across this resistor. And so if you go along the same direction as the current, which in this case is clockwise, anytime you come across an element like a resistor or a capacitor, there's going to be a negative potential drop across that element. And so now we're done with the resistor. Now let's go into the capacitor. And since we're going clockwise, we now encounter the capacitor, and so there's going to be a negative potential drop across the capacitor as well. And then all of that is equal to 0. Because after the capacitor, there's no more elements. We just return back to our original starting point. So this is Kirchhoff's loop rule. And so let's expand this out a little further. So the formula for the voltage across the resistor as a function of time is just equal to the current in the circuit times the resistance of the resistor. And note that I wrote the current as a function of time because the current through the resistor varies with time. That's why I denoted the current as a function of time, because the current is varying with time. And so at time equals 0, the current is the maximum, or the current in the circuit is at its maximum. At steady state, the current is equal to 0. And so the current in the resistor, or the current in the circuit, is actually varying. And so that's why I wrote it as a function of time. And the same reasoning applies to the voltage across the capacitor. The voltage across the capacitor is equal to the charge on the capacitor plates over the capacitance of the capacitor. And I'm going to write this charge as a function of time. And the reason why I wrote that charge as a function of time is that because initially at time equals 0, the charge on the capacitor plates is 0. But at steady state, the charge on the capacitor plates is at its maximum. And so the charge is varying with time. And so that's why I wrote the charge as a function of time, because the charge is going to vary. Now, over here I wrote the current as a function of time, but remember that the current is just a certain amount of charge per unit time, which I can denote with dq over dt, which represents a small amount of charge over time, over a small amount of time. So I can just substitute in dq over dt for the current as a function of time. And then after substituting in dq over dt for the current, let's bring that term over to the right-hand side. And if I do that, it would look like this. And so all I did was just to replace the current with the dq over dt. And notice how that term is multiplied by r, and I want to get rid of that r, so let's divide both sides by the resistance r. And if I divide both sides by r, then the two terms on the left would get divided by r. Now, I just rearranged this. Now let's combine these two fractions into one fraction, and we can do that by cross-multiplying. So if we cross-multiply the voltage of the battery times RC, and then subtract that from R times the charge, and divide that by R times RC, we would get the following. So all I did was just cross-multiply the two fractions. So I multiplied the numerator by the denominator of the other fraction, and then subtracted that from the denominator times the numerator of the other fraction. And remember that all of this is equal to dq over dt. And now, let's bring this dt variable over to the left-hand side, and we can do that by multiplying both sides by dt. And let's bring this numerator over to the right-hand side by dividing both sides by this numerator. And if I do that, I would get the following. If I multiply both sides by dt, I would get the following. And if I divide both sides by this numerator, I would bring the numerator over to the right-hand side. So it would look something like this. And also, let's factor out an r from the expression. So if I factor out an r, it would look like this. And notice how both sides have an r, so I can cancel those out. And so the remaining expression would look something like this. Now notice how both sides have a dt and the other side has a dq. So in order to get rid of these two expressions, or two of these variables, we would have to integrate both sides, because dt and dq just represent a small amount of an element. So dt represents a small amount of time, and dq represents a small amount of charge. So in order to get rid of those, we would have to integrate both sides. And if we integrate both sides, we would get rid of the dt and we would get rid of the dq. And let's define the bounds of integration for the right-hand integral. So notice how immediately after the switch is closed, the time is equal to 0. And so the lower bound of the integral, or the lower limit of the integral, is 0. And let's just set the upper integral to any time t, because we're solving for the charge on the capacitor as a function of time. So we'll just set the upper limit to any time t, because we're finding the charge as a function of time. And so if I take the integral of the left-hand side, notice how RC is just a constant. So I can just pull that out of the integral since it's a constant. So it would look something like this. And since RC is a constant, I pulled it out of the integral, and the only thing I have remaining is the integral of dt. And the integral of dt is just t. And I still have my constant remaining. So this is the final result of the integral on the left, which is this integral right here. Now let's solve the integral on the right-hand side, which is this integral right here. Now, in this integral, notice how the voltage of the battery times C is just a constant. And this variable right here, the charge as a function of time, that's the variable. And that's the variable because this numerator right here is what we're taking the integral with respect to. We're taking the integral with respect to dq of t. So let's write a similar integral that's easier to look at, that's similar to this integral right here. So let's say instead of q, we use the variable x, just so it's easier for us to see. And this term right here is a constant, so we can just choose any arbitrary constant for our alternative integral, and this term right here is just the variable. So the variable that we chose is x. So notice how this integral and the other integral are very similar. So now let's solve this integral that we came up, and then our answer for the previous integral will be similar to this integral. So let's solve this integral right here, and whatever answer we get for this integral, that answer is going to be similar for the integral that we had previously, which was dq over the voltage of the battery times C minus Q of t. So let's just solve this simpler integral, which is easier for us to look at. And so in order to solve this simpler integral, we would have to use u substitution. And in u substitution, we would have to set our u variable equal to something in our integral. And so let's set the u variable equal to the denominator, which is 4 minus x. And then we have to find what is the derivative of u with respect to x. Now, if we take derivative of u, the derivative of a constant, which is 4 in this case, is just 0. And the derivative of minus x would just be negative 1. And so the derivative of u with respect to x is just -1. And if we multiply both sides by dx, what we get is that du is equal to -dx. And now let's substitute in all of these u variables into our integral expression. And if we substitute in, so we need to substitute something in for dx. And so let's solve for dx here. If we isolate dx, we notice that dx is equal to -du if I bring the negative sign over. And so I just substituted in dx equals -du. And the denominator right here is equal to u. So u is equal to 4 minus x. And so this is our integral in terms of u variables. And notice how there's a negative sign, and I can pull that negative sign out of the integral since it's a constant. And so what I'm left with is the integral of du over u. And so the integral of du over u is just equal to the natural log of u. Or in other words, the integral of 1 over u is just equal to natural log of u. And so remember that the u variable was equal to 4 minus x. And so if we substitute in 4 minus x for the u variable, what we actually get is this final expression. So the result of this integral right here is this expression right here. So the integral of 1 over 4 minus x is equal to the negative natural log of 4 minus x. And so now let's use this result to solve this entire integral right here. And we can use this result because both of these integrals are very similar in that they have a constant term and a variable term. So let's just use this result to evaluate this integral right here. So notice how in this simplified integral, the 4 represents the constant term, and the x variable represents the variable term, which is q of t. So if we just use this answer right here, we have that the negative log, or the negative natural log of the constant term, and the constant term is just the voltage of the battery times C, minus the variable term, and the variable term is just q of t. And also, so this is the result of the integral above. And so notice that it has a constant and a variable term. And so the limits of our integral are from t equals 0, or time equals 0, to time equals t. So we had to take those upper limits and lower limits into account when we define our integral, or when we find the result of our integral. So we would have to write in the limits like this. And so the result of our integral expression is this right here. So the integral of this circled integral is this bottom result right here. But now in order to solve this, we have to use the limits of integration to plug the limits in, and then we can come up with a final result. Now let's plug in these upper limits of integration and our lower limits of integration into this variable t in our integral result. And so if we first plug in the upper limit, so let's plug in the upper limit. And so the upper limit is t, so we just plug in this variable t into this t right here. So the expression is still the same. And that's minus a minus natural log of the voltage of the battery times C minus Q of 0, because now we need to plug in the 0 into this T right here. So let's plug in the 0 for a T. And so now let's simplify this down. And so notice that there's a minus minus, so a minus is just a positive. It would turn both of these signs into a positive. And let's just bring this term into the front, and let's bring this term into the back. So if I switch these two terms, and also notice that I have Q of 0, and the charge at time equals 0 is just 0. Because remember that at time equals 0, there is no charge on the plates of the capacitor. And so the charge at 0 is just 0. Or the charge at time equals 0 is just 0. And so let's just switch these two terms around. Okay. And so all I did was just switch these two terms around, and now I get this final result. Now let's simplify this final result down a bit further. Notice how I'm subtracting two natural logs. Now, and since I'm subtracting two natural logs, remember that if I have log of A minus log of B, if I want to simplify this down, the difference between these two is just the log of A divided by B. And so I can apply that same principle to these natural logs. So since I'm subtracting these two integrals, the numerator will be the voltage of the battery times C, and the denominator will be the voltage of the battery times C minus Q of T. And so this is the simplified natural log. And so this final natural log expression right here that we came up with is the result of our earlier integral right here that's circled in red. So the earlier integral that's circled in red, we evaluated that into this final expression right here. And so now that means that, and remember that T over RC was the result of this integral right here. And so this integral equals this final result right here. So we can just write this result in. So the right-hand integral equals this final expression right here. And so both of these integral expressions equal this result right here on the right hand side. And remember that we're trying to find the charge of the capacitor as a function of time, meaning we want to solve for this variable right here that I circled. And so we need to isolate this variable. But notice that there's a problem, because in order to isolate that variable Q of t, or the charge as a function of time, we have to get rid of this natural log first. And in order to get rid of a natural log, let's say that we have a function that's like natural log of x, how do we isolate the x and get rid of the natural log? And let's say that y is equal to the natural log of x. How do we get rid, or how do we undo the natural log? And the way to undo the natural log is just to raise the natural log of x to the e power. If we raise both sides of this equation to the power of e, then the natural log and the e would cancel out since they're inverse functions. So the inverse of the natural log of x is just e to the x. So that's why we would have to raise both sides to the e power in order to undo the natural log. And notice how doing that isolated the variable x. So now we have to just apply that same principle to our earlier expression right here. We would have to raise both sides to the e power, and notice how that cancels out the e and the natural log. And now let's write what we have remaining. We have e to the power of t divided by rc, and that's equal to, remember that we got rid of the natural log and the e, and so all we have left is what we have in the circled circle, or in the circled expression. So we have that the following expression. And remember that we're trying to solve for q of t. We're trying to solve for the charge as a function of time. So we need to isolate that. And in order to isolate that, let's multiply both sides by the denominator to bring that over to the left-hand side. And let's divide both sides by e to the power of t over rc to bring this term over to the right-hand side, or to the denominator of this term right here. And if we multiply both sides by the denominator, we get the following. And if we divide both sides by e to the power of t over rc, we bring that term over to the denominator of the right-hand side. So it would look something like this. And remember that we're trying to solve for this variable q of t. So let's add that to the right-hand side. And so then we'll bring q of t over to the right-hand side. And let's bring this term over to the left-hand side by subtracting it. And if we do all of that, we get the following expression, that q of t is equal to the voltage on the battery times C minus the voltage of the battery times C divided by E raised to the power of T over RC. Now notice how both of these terms on the right-hand side have variables in common. Both of them have a C and a voltage of the battery in common. So we can factor those two variables out. And also notice how I have E in the denominator. I can bring that to the numerator by negating the power. Or I can just flip the sign on T divided by RC, making it negative, and that would bring that to the numerator. So let's factor it out, or let's factor out the common variables. The two common variables are the voltage of the battery and C. And if we factor out those two variables from the first term, if we factor out those two variables from this term right here that I circled, the remaining expression is just 1. And if we factor out those two variables from the circled term in the numerator, we would just get 1. And remember that we're flipping the sign on the e raised to the t divided by rc. And so that would make it negative. Since we're bringing it to the numerator, we're just negating, or we're just flipping the sign on the exponent. And that allows us to flip the e to the numerator instead of it staying in the denominator. And so this expression right here is the charge on the capacitor as a function of time. So the charge on the capacitor as a function of time is given by Q of t is equal to the voltage of the battery times C, parentheses 1 minus e raised to the negative t divided by RC. And so that's the charge on the capacitor as a function of time. Now we need to find the current in the resistor as a function of time. In order to get the current in the resistor as a function of time, we need to recall that the current in the resistor, or the definition of current, is just that it's equal to a change in charge over a change in time. Or in other words, this change in time just means delta time, or a change in time. So we could just replace those delta signs with dq and dt, because dq and dt represent a very small change in time and a very small change in charge. And so this is the definition of current, that current is a change in charge over a change in time. And since the current is a function of time, I'm also going to write that the charge is also a function of time, since the charge is changing with time. So another way to rewrite this is that the derivative with respect to time of the charge is equal to the current. But now we're taking the derivative of the charge with respect to time. But remember that we already found the charge, and it was given by this entire expression right here. So all we have to do is just take the derivative of this circled expression, and then we would get the current in the resistor as a function of time. So if we just take the derivative of this circled expression with respect to time, we can solve the question. So let's just take the derivative of this with respect to t. And if we do that, we would get that the derivative with respect to time of the charge of this entire expression, if I write it in right here, it would look like this. And notice that since we're taking the derivative of this expression, we can take out this constant, which is the voltage of the battery times C, since it's just a constant. And we can take that out of our derivative expression. And so what we're left with is the following. And now let's take the derivative of what's inside the parentheses. Now the derivative of 1 is just 0, because 1 is just a constant. And so another way to write that, just so we can see it better, is that since we want to take the derivative of the two terms on the inside, we can take the derivative of each separately like this. So let's take the derivative of this second term right here. It would look like this. And remember that I said that the derivative of 1 was 0, remember? And so if we simplify that, we have 0 plus the derivative of this second term. And so if we want to take the derivative of this expression right here, notice that there's a negative sign and we can just pull that out of the derivative. And if I rewrite that, then if I pull the negative sign out of the derivative, all I have remaining is the circled expression right there. So what I have remaining is the following. And so I have the derivative raised to some negative power. Now, how do I evaluate the derivative of e raised to some negative power? Now, let's look at a different example of e raised to some negative power, and let's take the derivative of that. Let's say we have the derivative with respect to x of e raised to the negative x. And how would we solve this? And so remember that the derivative of e raised to some power, that would just give us e raised to the same power. And so, which is just the original expression. But remember that we have to multiply by the derivative of the numerator because of the chain rule. So we have to multiply the derivative of negative x. And if we do that, we get that e raised to the negative x times the derivative of negative x is equal to the following expression. So let's apply that same principle to solve our derivative expression right here. So if we rewrite our expression, we have the following. And so remember that the derivative of this e raised to this negative power would just the first term is just e raised to that same negative power, and then we need to multiply by the derivative of the numerator, right, of the exponent, sorry. We need to multiply by the derivative of the exponent, which is circled in red. And so let's multiply by the derivative of negative t raised divided by rc. And notice how in this derivative expression that rc and the negative signs, all three of those variables are just constants. So we can actually just pull those out of our derivative expression. And if we do that, the only thing we're left with is, and we can also bring the negative sign out of our derivative expression. And if we do that, the only variable that we're left with is t. So what we're actually asking for is, what is the derivative of t with respect to t? And the answer to that is just 1. And the derivative of t is just 1. And then the only thing remaining is this negative sign and the denominator, which is rc, since those are constants. So we can just pull those out of the derivative expression. So if we do that, our final expression looks something like this. And so the derivative of that expression is just 1 over rc. Now because the derivative of t is just 1. Now let's simplify this down further. Notice that there's two negative signs, so a negative times a negative is just a positive. So we can get rid of those two negative signs, And we can further simplify this because the C and the denominator of C will cancel out. And so what we're left with is that the current as a function of time is equal to the voltage of the battery divided by the resistance R times E raised to the negative T divided by RC. And so this is the final expression for the current as a function of time. And so these are our final two results of the charge as a function of time and the current as a function of time. And so these are the two answers to the last question. And just to clarify, these two equations only apply to a circuit in which the capacitor is charging. Or in other words, we can only use these two equations that we derived when the capacitor is charging in a circuit. And in this case, the capacitor was charging because initially the charge on the capacitor was 0, and then at steady state the capacitor reached some final charge.